Welcome to this CodeRage 9 session, the Parallel Programming Library Architecture with Alan Bauer, Embarcadero Chief Scientist. Hi, Alan.
Hello.
New in XE7 for Delphi C++ and Rad Studio, and also for Appmethod September 2014 release, is a new parallel programming library, which is available for both the Object Pascal and the C++ language, and works across all the target platforms that we work with. So, Alan, maybe you could give everybody just a few of sort of introductory thoughts about, number one, parallel programming in general, and also a little bit about what was going on and what you were thinking about when you started doing the design and implementation of the library.
Well, it has a bit of a history to it. I've done a lot of work over the years in parallel programming and looking at a lot of the developments going on there. I've actually followed a lot of the different developments of things such as the Silk, the thread building blocks from Intel, and the task parallel library from .NET. And more recently, been looking at the Grand Central Dispatch that Apple released several years ago. And so all of these different technologies, they have slightly different viewpoints. Of all of them, the sort of the task parallel library stuff from .NET felt much more natural to a Delphi-centric view and to how Delphi would typically be done. And so a lot of the parallel programming library was somewhat modeled after some of the .NET idioms and the way that library works.
But we've had things like asynchronous programming, right? We've had multi-threaded application development. We've had early chips that only had one processor, so what can you do? How does this relate to the world of parallel programming and the library?
Well, what is, as many people know, is that rarely do you buy a computing platform these days that consists of a single CPU core. Even the phone that's sitting in your pocket typically is going to have at least 2 cores on it, sometimes even more. The tablet or the phone-sized tablets and everything, they typically are going to have multiple cores. Desktops, you can't hardly find a desktop that has anything less than 2 cores these days. Even years ago, when they started predicting all of this, at the rise of the multi-cores, people are going to want to start taking advantage of them. We've had things like multi-threading and asynchronous type concepts in the past, but the thing is that threading and parallel are not necessarily the same thing. Parallel is really about utilizing the CPU core in the most efficient, or cores, in the most efficient manner. Threading is about breaking up bits of work into separate threads of execution. Now, parallel is typically implemented using threads under the hood, mainly because the operating system is the one scheduling these threads onto the different cores and then running them simultaneously. Parallel is more related to threading in the sense that threading is used as a way of getting to parallel. If you're not on a multiple core machine, nothing really occurs in parallel at that point. You still have to slice things up and then schedule them onto the same core over time.
Sometimes I think about, in this modern world of graphic processing units, GPUs, what's my favorite one? The NVIDIA Tesla card. You can get them in different sizes, 1,024 GPUs, even more GPUs on a card. Some people use that for graphics, of course, and really great games, but there's this whole world of GPU computing. The parallel you're talking about here is not GPU computing, right?
Correct. Yeah, we're talking about the actual general purpose CPU, the main CPU core that the operating system uses to actually execute itself and to execute user programs. And so we're scheduling onto the CPU, the general purpose CPU in the system. The GPU itself, those are highly tailored for computational, massively parallel computational tasks, in which graphics are massively computational and parallelized. But they're much more tailored for those types of operations. Now, of course, people are using the GPU for general purpose computing and taking slices of functionality and pushing them into the GPU. This library doesn't currently approach that at all, and it is something that we've looked at and have been considering, looking at some of the OpenCL things and the open graphics things to be able to push those kinds of things there. But it's a different programming model, even from normal parallel programming that we're doing on the CPU. but it's an interesting thing to look at.
And I know there's other systems like OpenMP. There's other libraries that people have had for multiprocessing. Those still exist in their worlds and on their platforms as well, right? Whether it's Linux or Unix or other places.
Yeah, correct. Our library is just that. It's a library. There's no core language integration at this point. Part of the reason for doing that is we want to get the library itself and the core mechanics for the library across the different platforms nailed down before we start committing to specific semantics that the language may want to inflict on that or do that. And if you start making mistakes at that point or start wanting to shift things around because you want to say that this is a better solution, you can't really change semantics of how the language itself works, but you can change semantics of how a library works and evolve that much more readily than you can trying to change syntax of a for loop within the language itself to introduce new semantics because you can't affect the old semantic. It's actually much more limiting by having a language integration. It sounds great on paper, and a lot of things are doing it. Like you have Silk is doing that. The OpenMP stuff is language integration things. They're focused more on very small pieces of what we consider parallel programming itself. I'm looking at much more broader uses of the parallel programming, introducing an asynchronous programming better into the language or better into the libraries, in addition to doing general computational tasks in parallel as well.
Is there any magic tool that you have, Alan, that will take my code and parallelize it for me?
Unfortunately, the panacea of the make my program faster switch just doesn't exist. There's been a lot of research in this area, both in academia and in the industry itself. I mean, I follow some of the guys out of Microsoft that do a lot of this and out of Microsoft Research. They've yet to find the magic pixie dust that they can just sprinkle over your program and it makes it, suddenly figures out where to make things parallel and all of a sudden it works.
So maybe then we'll switch over to the parallel programming library that you've implemented and that is part of, again, the latest releases of our products. As you mentioned, there's this new unit with the interfaces in Object Pascal and C++ as well with the system threading namespace. In Object Pascal, the unit namescope system.threading. It's the same library with the same capabilities on all four platforms we support, Windows, Mac, iOS, and Android?
Correct. If you look inside what we ship, I don't believe there's any if-defs whatsoever in the code, even in the implementation between the different platforms.
Okay.
So it's built on top of all of the low-level cross-platform functionality that we've already introduced into the libraries and into the tools at this point. And so there's no need for any kind of if-defs or uniqueness across the various platforms because it's actually built on top of, like I said, it's built on top of the T-thread is there. It's built on top of any kind of synchronization or things like that. It's all based on some of the core synchronization objects that we've added over the years. There's no need for having a different implementation or having something. So you can be fairly assured that you're going to get same semantics across your different platforms. The only differences may be in terms of how the threading model on a given platform, how the OS schedules threads, may be a little different depending on the platform. And yeah, I mean, when you start using the library and as you start scheduling more work into all the different cores, other things start happening that you typically don't think about, but you have to start thinking about in terms of power dissipation and battery life and things like that. So as you light up more cores, it takes more energy. You got more transistors switching inside the CPU. It starts burning more juice. And so, if you're going to run a long-running parallel process on your quad-core phone, don't expect great battery life.
So getting back to, I mentioned earlier that I was looking for this magic tool that would, in a sense, parallelize my applications. But if I look at the implementation of the parallel programming library, you're giving me some hints in how it's implemented. There's a parallel for loop. So if I've got for loops in my application, I can start thinking, gee, I wonder if I could parallel parts of the insides of those. Correct.
Yeah. The idea is that you can look for opportunities to put things into parallel, especially if you're doing computational type operations over an array of things, matrix type things, or even what if you're going to process a bitmap that's maybe you want to do that on the CPU, you want to do some sort of an effect on that on there, and so it's an array, and so each individual cell can be considered individual, and so you could actually break it apart fairly easily, make that parallel. When you're doing things in parallel, you still have to deal with synchronization and other types of things, but you got to be careful about that, because as soon as you start introducing synchronization objects into your parallel loops, you actually start destroying the parallel nature of things, because as you block operations on a given computation, waiting for something else to happen, that thread can't be doing anything else at that point. So it's blocked, waiting, and so that core suddenly is going to be scheduled off doing something for some other program and not yours, and so it's not going to be able to as effectively use the cores as it could. You have to look at your data more than you do about your actual program and the actual statements that you have, but you have to look at the data. Can the data be done in parallel? And so the prime example, I wrote, that's one of the first examples, which is just a simple example of Conway's life, which is just a grid, and then based on the current status of the grid, that determines what the next generation of that grid is going to be. And so while the source grid is static, the new destination grid is what I'm constructing, but I'm actually constructing each individual cell based on the previous generation independently of all the other cells. So there's no dependencies across any of the different loops. So you can actually schedule all of those things and parallelize the generations, the generation calculations of for the Conway's life. So each cell can be determined from its previous generation independently.
And I know some of the other examples we've done things like finding the prime numbers between
Correct.
0 and choose your favorite highest number. Those calculations can be parallelized and thrown out to the different processors.
Correct. Yeah. So little things like that are very eminently parallelizable. You can't really make blanket statements as to this is parallelizable, not, because there's so many different things that you can rearrange how you approach the problem in a way that makes it even more parallelizable. So it's really going to be up to other people, the users or the developers, to actually decide how to do that. And I would really encourage people to start reading up on not only just threading, but also on parallel processing and library, things like memory models and concurrency and things like that. So there's a lot of little subtle things you have to be aware of. And most of the stuff that's in the library and the operating systems kind of shield you a little bit from some of the real niggling, low-level stuff, but you still have to be aware of them.
In the prime number generator, I had a global variable that was counting the number of primes being found. So I needed to make sure I was synchronized properly when I was going to increment that global count across all the different
Correct. Yeah,
parallel
you do need
fours.
to. There's different granularities of locking, and so when a lot of people, they think of critical sections or mutexes as being this, as being a sort of the smallest granular thing, but you actually have much even smaller than that, where you can run. Most processors allow some level of atomicity for operations, and so on small slices of data, and so like an integer can be incremented atomically, which means that no other parallel core can be also incrementing that value until it is done incrementing. And so when the next core wants to try and increment it, has to actually stall that core slightly to increment it as well. Some processors, like the Intel processor, as long as you're aligned properly in memory, a increment instruction is going to be atomic, but you're not guaranteed atomicity because you're not necessarily guaranteed the alignment. Other processors do different kinds of things. ARM, for instance, has a different mechanism for guaranteeing atomicity, and it's actually a multiple instruction thing rather than just being a simple modification of an existing instruction like on the Intel to implement a synchronized increment, whereas the ARM, it's a little bit more complicated.
Or maybe user interface, I'm updating some edit box or some UI element of a VCL app or a FireMonkey app. In that case, if the different cores want to go at the same areas, we'd want to synchronize something, right?
Correct, yeah. And typically, though, what I would recommend is that from within your parallel loops or the task or whatever you're doing, if it's just a standalone task that you want to schedule into the thread pool itself, or you have a future, and we can talk a little bit more about those, but in terms of just doing loops like parallel for loops, in general, you want to complete that task before you start really notifying anything. Because as soon as you start trying to notify other other outside things, you have to introduce some major synchronization things, especially if you want to synchronize against the UI thread. And so in that case, it literally has to block waiting for that to occur. Now you can queue events in there and it won't necessarily block, but there's still a little bit of overhead in just queuing up an event into the global synchronization queue. If, for instance, the game of life thing that I wrote does no updates until it's actually calculated a generation, whatever big the board size is and the world that you're calculating, it doesn't do any kind of synchronization or any kind of notification as it's working until it's done. Well, the idea is that it's going to happen much, much quicker, so you don't need to really keep the status update during the middle of that time.
We'll come back to Parallel 4 in a moment, but I wanted to make sure we talk about the two other major areas in the parallel programming library, tasks and futures. And future is related to tasks, right? So maybe tell people a little about what a task is, what an interface to a task is, and then what a future is and how it relates.
We start from sort of the low level. The first thing that the library introduces is the notion of a thread pool, which is just a general purpose thread pool, and you can actually schedule work into the thread pool independently of tasks or anything like that. So you can schedule work into the thread pool. And the thread pool is self-tuning. It figures out how many cores you have. It will, based on the load on the CPU, it'll actually add threads if it needs to. So say you've scheduled a task into the thread pool and it's taking a long time to run, or maybe it's blocked waiting on something. So it may actually decide that I need to add a thread into the thread pool because I'm not really utilizing the CPU as well as I could because some other thread is currently being blocked. And as the CPU usage then goes up above a certain point, it'll start aggressively trying to retire threads as well. And so it'll shuffle the work off from a retired thread back into other queues within the thread pool, and then they'll start taking over that work as well to try and not oversubscribe the CPU. So if you've got 2 cores, you don't want to run 100 threads that are all actively doing something, because just the thread switching overhead will destroy any kind of performance improvements that you have. So it's better to actually, if you're going to serialize stuff, it's better for the user's program to serialize that and break it up based on how many cores it has than the CPU to try and do that. It can't easily figure that stuff. You break it up into small enough pieces in your various tasks and bits, it can more efficiently schedule across the different cores.
What is a task?
A task is a unit of work.
Okay.
So if you just think of a task as just it's something that you need to get done, and generally it's going to be independent. You don't care what thread it's on, you don't care what core it's executing on, you just need this work to be done. Now, knowing that it's going to be executing possibly on a thread that isn't the thread that you actually are currently executing on, either the main thread or whatever, whatever task it is, it needs to also be aware of the fact that it's going to be executing potentially on another thread. It could still actually execute on the current thread as well, but it's up to the thread pool and the task itself to figure out how to schedule things into the thread pool. So you still have all of the normal traditional constraints of threading, but the task allows you to break things up, and then it will schedule into the thread pool. You don't have to worry about creating threads. You don't have to worry about managing your threads. So you can just create the task. It'll run a certain bit of functionality, and then the task can be completed, and you can wait for it, or you can wait for it to finish.
So it's an object. It's a class.
It's a class, but you really interact with most of the things in the task portions of the library through these interfaces. You'll request that a task be created with a given bit of work, and it's going to return in this interface or an iTask interface. Okay. And so on that, you can actually wait for the task to complete, or you just can hold on to it, or you don't have to hold on to it at all, and it'll eventually just finish itself, and it'll go away and clean up itself. So the idea is that either you can hold on to the task, or you don't have to hold on to the task. And being an interface, it allows that flexibility. The same for things like the future. You don't actually create the future objects yourself. You let the thing and it returns a future. And a future is slightly different from a task, to where, say you need to calculate some value, or you need to run some query, or you need to operate on something. But meanwhile, while that's working, you want to do some other calculations, and so you don't necessarily need the result right away, but you know at some later time you're going to need this result. And so you can schedule a future, which it's a generic interface, and so you schedule it based on the type of the thing you want to calculate and return. You provide it with a function or a method that actually does that calculation, and that's what's scheduled as a task. And then once it's done, it returns the result, and then you can request the result. If the result's not available by the time you request it, it will block waiting for the result to be available.
So that's done under the covers. I don't have to issue some wait command or some sit there in some polling.
No, you just
say,
I need to get my value now because I need it now. And if it's not completed, you'll block waiting for it. Now, you can ask to see if it's done and keep going if you want, or you can poll it if you want to. That's all possible. Or you can even block waiting for the thing to complete. So, because a future is really just a derivative of a task. Okay. It just has specific functionality.
So in tasks, when they get started, the tasks are started. Maybe I create an array of interfaces for tasks, and I start a bunch of tasks, go off and run some functions. What choices do I have to either wait for? Like, I need all those tasks to complete so I can move on. I can do something.
There's functions that allow you to pass that array, and you can ask to say, return when any of these tasks complete, or return when all of the tasks complete. It's sort of a wait for multiple kinds of a thing. And so you can wait for any of them, you can wait for all of them. If you wait for any of them, it'll tell you which one, the first one it figured out that completed. And if you're waiting for it and it got completed before you even finish the wait, it'll immediately return on a wait for any and a wait for all and a wait for all of them.
So when I have an array of tasks, does each task have some status field somewhere so I can see which tasks are done? Maybe I want to update the percentage of tasks completed as a user interface or something. Can I?
Yeah, you can query the state of the task. Is it being completed? Is it even pending? It could not even have been scheduled yet into the thread pool because so many other tasks are going on, and it could just be there waiting to be scheduled or waiting to actually be run. It's sitting in a queue somewhere and ready to go.
In all these cases, the parallel for loop, the tasks, the futures, are those the three major parts that an application developer might use, or are there other parts of the parallel programming library?
Those are the major portions of it. There's the idea is to provide as simple of a sort of a design that gives you a lot of power with very little confusion and stuff. Lots of different little things. So, but even then, there's a lot of little options you can do. For instance, the parallel loop, you can actually iterate over various ranges of things, and also control the loop itself like you would typically control. So you could, suppose you decide you need to terminate early, so you can actually get a sort of this loop status or internal loop status that gets passed to your looping function. In addition to what the current index you need to process is, you can actually tell it, I need to cancel or break out of this loop, which is an interesting problem because you have other threads are also running other iterations and things, and so they may need to either complete or finish up somehow, but then once control is returned, it's going to go back through the next iteration of whatever thread is actually executed, whatever portion of that process is done. And if one of them decides I needed to break out of this loop, it'll return to you as a sort of a result that will say I was able to execute. This is the highest index I was able to execute. That doesn't mean that every index between the lowest starting and that highest iteration actually did run. It just means that this is the highest one, because it could interleave across the whole range in different ways depending on how things are scheduled.
So parallel for, if I remember correctly, I remember when I was in the ID and I tparallel.for and then I put left parenthesis, a whole bunch of choices come up. But I think the common ones are there's probably the first 4 parameters, maybe.
There's a lot of overloads depending upon how you want to actually run the thing, and so you typically give it the low bound and the high bound, and it's modeled after a normal Delphi for loop, which is it's low inclusive and high inclusive. You go from the low value to the high value, and then there's what's called a stride, and a stride is more or less a way of pre-tuning the for loop. If you have a fairly small set of iterations you need to do, you probably want to pick a smaller stride. You actually don't need to even really worry about that. In general, you want to only use the stride if you've got a large number of things and you want to pick a larger stride out of the gate so you get better disbursement across your work process and everything. So if you're doing a parallel for loop over, say, 100 items, you may not really need a stride of more than 4 or 5. So what it does is it breaks it up, and the stride is how far apart from each iteration does each thread get scheduled. The farther apart they are, in general, that keeps for a lot of different cores, that keeps the different CPUs sort of from stepping on each other, because a lot of times the data is going to be physically in memory located next to each other. And so by having a different stride, you can actually improve performance, because the different CPUs they're accessing different portions of the cache on the CPU, and so they don't end up with implicit inherent cache locks and cache line locks at that point. The stride is more or less sort of self-tuning as well. So if you start with a low stride, you just pick one at the start. For loops that have just, say, 10 iterations, it'll actually schedule as many as it can up to the number of cores that you have. So say you have 8 cores and you have 10 iterations. It may actually schedule 8 of those iterations simultaneously into the thread pool and then execute them virtually all in parallel. Whereas if you had picked a stride of much higher than the actual range that you have, it may only schedule a couple of different processes or different tasks to work across your entire loop, and it may actually be worse performance at that point. In general, if you let it tune itself, you're probably okay, because what it does is it tries to the first time through, it figures out that I'm going to try close together, because you may break out early or whatever, so I'm going to get as many scheduled as possible iterations, and then it'll actually lengthen the stride as it runs the process. So it'll lengthen up to probably about 128.
So what I wanted to do, Alan, is just bring up the ID real quick, and again, this session is for both, is in some ways language agnostic, but I'm going to bring up a Pascal example that has a for loop and a parallel for loop. This is the prime number example, just so we can see that here in the button click, we're just running through a for loop from 1 to some maximum and asking by calculating, is that number a prime number? And then incrementing this total number of primes found, and it's using the stopwatch object to calculate the time. And then over here on parallel for, here we say tParallel.for, and then we have several parameters. This is parameter insight on a parallel for. What are some of these options here that we're seeing on the screen?
Well, the biggest one is that you can pick either a regular integer or 32-bit integer range, or you can go to a full 64-bit integer range and stuff. So typically you're not going to, the integer range one is going to be the most commonly used one, so you can probably cut half of those overloads out. The other one is that you can see that there's different ones that take anonymous methods that you can call directly from Delphi, and the code that you're showing here clearly demonstrates the use of the anonymous methods. The other one is that if you just use normal method pointers, and from C++, you would typically use regular events because they're both supported on both as well, and anonymous methods aren't as easy to do there. So various different types of loop or iteration functions. Some of them take loop state, and that's what I was explaining before, is if you wanted to actually control the loop, if it needs to exit early, you can control where you're at and stuff like that. So you can still do essentially what is a break at that point. So if you need to break out of the loop, you can also determine if some other loop iteration has maybe raised an exception at that point. So you can determine that, or if for some reason one of the other loops decides it needs to cancel, and so you can tell whether or not one of the other iterations is either broken out or is requested some sort of a cancellation. So you can, in your own code, test that. If you got a longer running process, you can periodically check that value to go, oh, somebody's requested a cancel, and then immediately return at that point.
So I see here low inclusive, high inclusive. That's the range of the for. And then I see an iterator event as an example parameter.
That's the actual event that gets called per iteration. And you'll get passed in at least the index, the current index that this particular iteration needs to process.
So I can get the loop state. I can see what the current index value is.
Correct.
I want to stop or something.
Right. Then if you want to, like I said, you want to control the loop, you can break at that point. Okay. Or you can determine if something else is happening, or somebody's requested cancellation, or there's an exception that occurred in some other iteration.
And then I see a thread pool
Yeah, the thread pool, there's a global thread pool, and in general, you're not gonna want to create another thread pool, although you can actually instantiate another thread pool, and then you can pass that thread pool in. You can actually take the thread pools. They have some tuning parameters in terms of the maximum threads they'll create. They'll still both try and load balance based on the number of how much CPU load is occurring. But it will, you could, for instance, decide I want to schedule half of my cores into one thread pool and another half into another thread pool, and then independently schedule things into them based on maybe two different sections of your application, and you want to keep them independent. Again, those are all scenarios that are going to be based purely on the developer's decision, what they think is going to be best for their application. In general, I would say that clearly the 80 to 90% case, the default global thread pool should be sufficient.
Now, I know that in a regular for loop, if I choose to, I can choose to either break it or exit from it, right?
Right.
And that's
what the loop state is for. So if you needed to break out of the loop, that's how you would do that. Now, because you're actually executing each individual portion of the loop, you're not technically in a language for loop. So things like exit is just going to exit out of that current iteration because it's just a function call. Break would just, if you're not in a loop within your loop, your iterator, that's not going to do anything for you. Continue doesn't really mean anything. So in those sense, continue is just you return from the iterator and then it just goes to the next one. Break, you have to actually tell the loop state you have to use the one with the loop state, and you just tell the loop state dot break, and you say I need to break, and then you return at that point, and you just exit, and then exit. You can't really, if you have code in there where you run through a loop and you exit out of your function completely out from within the loop, you have to do some things a little different. So you have to then break the loop as quickly as possible, and then just return, and then it'll still come out of that. So some of the more languagey stuff there's really no direct analogs. You got to do a little bit more work, but it shouldn't be difficult for people to figure out.
And again, if I've got a bunch of things running, can I cancel them all? Is there some call that I can say cancel everything that's running? I need to go do something else.
Right now, there's no cancel lots of things at once. Right now, that's one of sort of the future kind of things we're looking at is introduction of what's called a cancellation token, which you can then pass around this cancellation token to various tasks, and they'll all be looking at this one cancellation token. So you can hold on to it, and you can say, anybody that has this token, that has a reference to this token, I want it, and then I can tell the token that it cancel, and then everything will then cancel at that point. Now, the for loop stuff sort of has an implicit cancellation in shared cancellation status in there, like at the break. If you want to break out, that will try and cancel as quickly as possible all the other iterations. If an exception gets raised within an iteration, it gets caught, but it also signals that you need to terminate all the rest of the iterations that are currently going on, and it will then you have from the parallel for function there is a loop result structure that you can then get that loop result structure, and in that can tell you what happened. So was there an exception or something like that? In some cases, if there was an exception or multiple exceptions, they'll get aggregated together, and then before the for loop actually returns, it'll actually raise sort of this aggregated exception on the calling thread, the one that actually initiated it, as if the exception had occurred within a non-parallel for loop. So exceptions are kind of a tricky situation because each individual thread has to catch them, and then we have to hold them and then aggregate them, switch them over to, put them into an aggregated exception and then raise that exception. And then you can figure out from there what happened.
Okay, and again, this was the Pascal code for the prime number sample. It's got the from 1 to the max, then it's using an anonymous method here to call, and then it's using tinterlocked.increment to bump the number of primes found.
Yeah, that's an atomic increment function itself. So that's been there for quite a while. That's in the synchronization objects
in sync objects.
Yeah, so that's been there for quite a while. The Delphi language itself supports across all platforms now. Supports a lot of intrinsic functions that are atomic increment and stuff, and a lot of these the T-interlock stuff is implemented that way, using just the intrinsic atomic increment stuff.
And this was code that just creates a task and has an anonymous method, runs for a period of time, starts the task. And then I guess here's this wait for all, right?
Correct, yeah.
Or wait for any, I guess was the other option there.
Mm-hmm.
Okay. And then there's another one in this example for a future that just says task future and whatever that type is that.
Yeah, that'll be the result type. In there is the integer. And then it returns a future that has an integer as the instantiated type.
And then, Alan, I wanted to bring up, this is one of the samples you built, which is the Conway's life simulation. And this is the C++ version. So here, inside of your life engine, you called it, there's a parallel 4, and here we're passing the low and the high, and then you have an iterator event. Here's the iterator event. Just takes a sender, and there you're passing in the index. Right.
And then it just calls the process.
And then it calls process cells. Okay. Yeah. So again, under the covers, it's the same, as we mentioned, it's the same implementation, same source code, compiled, the libraries compiled for each of the platforms.
Correct. We don't do anything that right now that is specific to a given platform, unless that platform only has a specific functionality we're trying to expose. In general, everything is done in a way that we're going to try and get it to work on all of them.
And again, you mentioned that the operating system's pretty reasonable about what's going on as far as scheduling cores.
That's a problem that's long been solved by the operating system, and so we might as well just let them, deal with that. And besides, in where our applications run in sort of the user space, we don't really have that level of control of how we schedule onto what CPU. Windows, you actually kind of do, because you can actually set CPU core affinity on a thread and things like that. But I'd be very cautious about doing that kind of stuff, especially within a thread pool thread. If you say, I only want this thread pool thread to be scheduled on this particular core, within that thread, you can really mess with stuff at that point.
And again, the thread pool self-tuning and the major features are the parallel 4, the task, and the future.
We'll look at, adding some more types of things in the future, adding more support for trying to parallelize other types of operations and things like, a common one would be enumerators.
Alan has done the Conway's Game of Life, which was from Scientific American.
I just picked something that I knew it was going to be very graphical and very parallelizable at that point. And it would be something that it was large enough grained in things to where, and it was something that almost everyone has encountered in their early computer science, or even a lot of people. I've figured it out back when I was even in high school and before. I've seen that particular type of programming.
And if you have our products both into samples, which is the user public documents, Embarcadero Studio 15 samples, under Object Pascal RTL, you'll see parallel library, and then you'll see a FireMonkey version and a VCL version. And then the shared code is the life engine code itself. Right,
the life engine itself that does the actual parallel processing and stuff, and that compiles for all the different platforms. Again, I segregated all of the UI bits into the different, the FireMonkey and the Delphi version, and then the actual life engine that does the generational calculation of Conway's life is in the shared code, and that unit compiles on all the platforms unchanged.
And then you've got a bunch of the sample life files for starting points.
Yeah, I found those. If you look at Conway's life and you Google through that stuff, there's a whole bunch of resources on that. In fact, there's sort of this subculture I found within the Conway's life, to where they're trying to find what is the most prolific and the smallest pattern that creates the most prolific thing. And actually the one that's there is the acorn.lif is sort of the one that produces the most prolific patterns from the smallest starting pattern.
And there's C++ versions. There's the life engine in C++. Again, it's in the user public documents, Embarcadero Studio, CPP, RTL, parallel library. Again, VCL and FireMonkey versions of the C++ samples. So any other last comments or thoughts?
Yeah, I would just recommend, there's a lot of resources available that really talk about concurrent programming and those things. There's a lot of stuff coming out of MIT labs that discusses that. And then a lot of stuff out of Microsoft Research did as well. I believe there's some Carnegie Mellon resources as well, some white papers in there. One of my favorite books is one written by Joe Duffy from Microsoft. They did the actual task parallel library for .NET, his team and everything, and he wrote a book called Concurrent Programming on Windows. It's a very thick tome. Don't be afraid of the fact that it says Windows, because there's huge amounts of information there that are completely agnostic to Windows itself. There's a lot of Windows isms and stuff, but it talks about C++ parallelism, it talks about .NET parallelism, some of the resources for just the general Windows APIs, but it also goes into general concurrency concepts in dealing with how you can actually reason out whether or not a particular set of instructions can be run in parallel, and so what kind of weirdness can occur when you have two threads executing through the same bit of code without either with or without proper synchronization, or do you care about synchronization or not? Because there's some cases where you may not even worry about it and think it'll still be correct. Other cases you do need to worry about synchronization. There's a lot of stuff out there, but I would really recommend really kind of learning about not just threading. Threading is very important in synchronization across threads, and when you need to synchronize, how things actually work. But in parallel programming, you also have to look at how you can structure your data in a way that is as most parallel as possible, so you can get as much benefit from that. And a lot of times that requires as little amount of synchronization as possible in order to gain the best performance. So that's why each iteration needs to be as wholly independent, that you can't have any dependencies across the different iterations, and so you get maximum benefit from actually going parallel.
It's your time now with Alan Bauer, so it's time for Q&A. You can put your questions into the Q&A log and go to webinar, and we'll take a look at the questions you come up with and see if we can answer them. And Alan, thank you very much.
All right, no problem.
Okay, great. We've got Alan joining us here in the studio for answering your questions. Is it possible to transfer a UML model using flow lanes describing communication between different T-thread classes from Delphi 2007 Architect to XE7 Enterprise, or am I able to transfer to RAD Studio Software Architect and import to XE7? I'm not sure that applies to parallelism, does it?
Yeah, I'm not sure. That sounds very domain specific.
Yeah,
and everything, not sort of general.
Sorry about
stuff.
Okay, so here's one that is parallel. I use tparallel 4 and set report memory leaks on shutdown to true and get a report of memory leaks on shutdown. Is that an issue that they need to be aware of, or have you heard anything about that?
Yes, and that's actually been fixed internally, and we're in the midst of working on updates, so that should be something that will be addressed.
Do we need to worry about race conditions, and how would we address that?
Well, you always, if you're doing anything multi-core, multi-threaded, there's always going to be issues of race conditions and stuff. So it really largely depends on how you've arranged your data and how you actually are accessing that data. So, it's going to be highly dependent upon your individual situation. So, race conditions, you still have to think about them. As I said in the regular presentation, the parallel library doesn't absolve you from having to think about parallel things. It just provides a framework that simplifies the process of that. You still have to do some work in thinking about how your data is going to be structured. So you can eliminate or not worry about race conditions.
What is the threading equivalent of a critical section to protect lists, etc.?
The threading equivalent of a critical section. Well, you can always use a critical section. You can use the built-in monitor support within Alt objects as well. So, I'm not sure that there's a threading equivalent. I don't know.
So you said use the monitoring support in T-object as well?
Yeah, the monitor support. Yeah.
How do you monitor tasks to provide progress feedback for the user?
That's going to be largely dependent upon how you want to, do that within your own application. You can post status information from within your loops into a queue, and then that gets reported. You can do things like you can synchronize from within your particular task, but then that introduces a large it blocks while it's synchronizing at that point. So it's going to be largely dependent on how your application needs that information or how you want to report it. probably the simplest way is to merely post the information into a queue that is then, the foreground will look at and update a UI based on that information.
That's a good suggestion, into a queue.
Mm-hmm.
Does Delphi have any GPU core access yet?
Not at this time. Other than there are some libraries that are available, open source or out there that allow you to access things like the GPU either through OpenCL or the CUDA libraries and things, but nothing that's actually built into the product at this point. It is something we're looking at, and we've been looking into doing that, and obviously through the FireMonkey framework, there is some implicit GPU access because you can do shaders and other things like that as well.
How would you interrupt a task or feature? For example, say I wrote a routine that would count the number of pixels in an array, or count if the number of pixels in an array are above a threshold. As the user changed the threshold, I want to kill the old one before starting a new one.
Well, while you're processing in some sort of a task, at that point, an individual task can be canceled. There is a way of canceling it, and then within the task itself, you can check to see if somebody's requested a cancellation of that particular task, and then you can pull that information through whatever your task looping is doing and check that and then break out.
Having a class declaring the main class in 3 different T threads that co-work with reading files and feeding the main thread new lines of text, could this be realized also using parallel programming? Also a class that do file writing, which may use as many as 20 different objects for writing different files fast. But I still use tthread, or could I switch tottask?
You could use the task stuff. Some of the advantages of using the thread pool or even the tasks is that you can sometimes eliminate the startup and shutdown costs of individual threads. So you could treat the thread pool as just a way of scheduling individual work items as just tasks into the thread pool, and the thread pool will help manage those threads. Now it will queue up all the tasks into the thread pool, and it'll dispatch them in whatever threads are available based on the number of cores that you have. So if you need specific ordering and priorities of stuff, you kind of have to manage some of that stuff yourself. Either you need to spool up your own threads and control that. But if you're not really as concerned about it, you just need the work done as quickly as possible, you can schedule them into the thread pool, and it will manage the scheduling as best as it can.
About the parallel programming library, are there any new features for creating long-running background tasks? Think state machine that will run an entirety of the application lifetime and communicating between the background task and the main thread.
With the parallel and the thread pool itself, there isn't really the notion of scheduling a long-running task into the pool. So in situations like that, you're probably best to spool up your own individual thread if it's intended to be long-running. That is something we're looking at providing, is being able to specify that this particular task is a long-running task, and it can actually schedule it into a separate set of threads, or know that there's a group of threads that are going to be long-running items, and it could actually spool up threads for you at that point that are outside the sort of high-performance pool itself. But again, most of it is going to be based on what your application needs are. The thread pool itself uses tthread objects internally, and so there's really no difference between a thread pool for tthread in that sense than any tthread you spool up yourself.
Are there any examples of fast sorting an array for, like a million units?
I don't think we have anything specifically for that, but we're welcome for suggestions if people want to post, come up with things to do, fast parallel selection sort or merge sort or something like that. That'd be great. Heap sort, whatever.
So are you going to write a book on parallel programming? I'm looking for more examples. I wrote a small program, but it seems to get the wrong number because I need to use thread synchronization. How do you call thread synchronization in a for loop, for example?
Well, I'm not planning on writing a book myself, but it's not necessarily specifically about parallel programming. Some of the resources that I mentioned in the presentation are actually very good resources, and I've used those resources, just in my own education and learning process as well. And so, I think there's a lot of information that's already out there. So, again, those resources are probably a great place to start.
So, is there any tips on how to synchronize or call thread synchronization in a for loop? I guess it depends on what you're trying to do with the.
It depends on what you're trying to do. I think in the main presentation, I did caution against trying to do heavy UI synchronization within some sort of a parallel for loop, because that will, by design and by necessity, actually somewhat destroy any kind of parallelism that you may want to do. And so, anytime you introduce fairly high-level synchronization, even critical sections or mutexes or some way of where you have to notify the main thread and you're waiting for that notification to occur and you're synchronizing with it, that actually puts in a large serialization block within your parallel, and you may not actually realize all the performance that you need. So synchronizing within a parallel for loop is something that you have to take very cautiously. And that's why I was suggesting there's another similar question that, the best course of action is to post any kind of status updates into a queue that the foreground thread will independently be able to pull things from the queue. Even then, you're going to end up with some synchronization issues while you're placing things into the queue and you're pulling things from the queue. A lot of times that's going to require some level of synchronization, and so you may actually see a drop in performance just through manipulation of the queue.
Is there a way to limit the number of processors that will be used by a parallel for loop? For example, we'd like to provide an option where our users could still use their machines, for example, email, while the program is cranking away.
You can create your own thread pool, and there are some tuning parameters, properties on a thread pool itself, and you can scale it back. You can determine there's properties that describe how many CPU cores you have. You can go through and adjust some of those things to keep the thread pool from oversubscribing things. So and leave enough of the CPU available. The operating system itself is usually pretty good at making sure that any threads are not going to necessarily overtake the CPU as much as could be.
Mm-hmm.
Windows is actually pretty good about this, to where you've got lower priority items that's threads that maybe not have run in a while, and it's across all processes, by the way. And so it will actually do priority boosts to threads that are lower priority, but they haven't gotten any scheduled time because you got higher priority stuff running, and so it'll actually boost those priorities. Other operating systems are they do similar things, I know, and so a lot of cases those things are operating system defined kind of behaviors, but you can still actually, if you create your own thread pool and use that, you can kind of scale back and say, I'm only going to use this many of your cores.
What is the preferred method of getting data back to the main thread from a T-task while avoiding pulling from the main thread or polling from the main thread with a timer or such? Synchronize from the task can be tricky, but it works if you're careful. Queue works as well. Is one step better, but what would you do?
Well, queue is probably better because it's going to schedule and push something into the foreground thread, but not block the particular task or the parallel thread itself. And so it'll fairly quickly be able to return, and that's probably the best way to do it. And that's another form of queuing, like I was discussing earlier, is that you can push updates into a queue, either something you create yourself or just use the normal T-thread queue if you want to update the UI.
In regards to stride/load balancing, can you provide some conceptual guidelines for where/how to implement with nested loops? For example, for x equals 0 to 100 do, parallel for y equals 0 to 100 do, versus parallel for on the outside versus.
Yeah, I think I see where this is going. In general, you want to try and you want to make the outer loop the parallel loop and the inner loop not parallel. That, first of all, that keeps from sort of oversubscribing and getting too much overhead and just tasks. But each individual thread can do that. As far as the stride tends to be a little self-tuning. It starts with you've got just a few iterations. It'll start with a smaller stride, which will try and do as many things close together in the range as possible. But as it works and as more and more operations are performed, it will widen the stride out up to a maximum stride. But you can specify an initial stride, which if you know it's going to be a large array of things that you want to process, you can start with a larger stride, and it'll tune up from there as well. So you can actually get the benefit of dispersing your work across the various portions of the range itself, and that allows you to keep things like CPU caches and cache lines from interfering with each other, because sometimes that can actually cause some performance issues as you're operating within the same cache line on different cores. Those internal to the CPU, it has to synchronize those things internally, and that you can actually affect performance. By having a wider stride, you may be operating on physically disparate memory locations and different cache lines at that point, and so the CPU can truly become much more parallel and operate within those ranges much better.
Application process messages. Should we use this when working with the parallel library?
Probably not. You would not ever want to use that. So that's a main thread thing only. If you try to call application process message from within a thread pool thread or just any background thread at all, you're going to run into issues because it's not going to do what you think, because each window handle on VCL stuff will only operate within the thread on which it was created in the first place. And so essentially a background thread doesn't have a queue or a message queue or or any kind of window handles associated with it. And so process messages would either hang or not even do anything.
Okay. And you wouldn't need to call it if you're putting the main thread, if you're putting everything in the background tasks.
Correct. Yeah, you wouldn't have to do anything. You just continue process. Now, if your foreground thread, you push a button and you want it to do something and you don't want it to return until it's done, but you want to do it as fast as possible by making a parallel for loop will automatically block anyway. But if you're trying to do a process messages within the body of a for loop, you're going to have to kind of rethink how you're doing that. Some of the things is that if you look at the life program that is one of the examples that I had written, is that it actually launches a thread, a normal T thread internally, and that's actually where it does the processing. But from within that thread, it then does a parallel loop, and that's where the work is actually being done. So the foreground is never blocked at any point. So when it starts running through the generations of the life board, it actually is running within another thread, and then that thread is launching other threads that are going to be parallelized, and then from that main background thread that's doing the processing, that's what synchronizes with the foreground thread.
So the next question is if UI manipulation is still tricky with threading. So that's still something you want to do in the main thread.
Correct. Yeah. In the presentation, I said that there's parallel libraries and parallel things. They're all implemented with threads. It's how it is able to schedule to the different CPUs. So all the same threading rules apply. So just because it's running in a task, you don't necessarily know that it's running in a thread. Likely it will be, but there are some cases where a task will be dispatched and actually executed within the current thread that you're running on as well. So the current thread that you're in is a likely candidate to be scheduled into, mainly for if you're going to schedule into the thread pool either through for loops and stuff. Sometimes it'll use the main thread itself or whatever the calling thread is as a way of scheduling tasks as well.
Is it possible to make parallel calls to databases through FireDAC or other mechanisms?
It's certainly possible. Again, the same threading kind of rules apply there. If you wanted to schedule a task and wanted to do some sort of query within a thread or within a task, it's really no different than spooling up your own thread at that point. It's just that you're leveraging the reuse of an existing thread in the thread pool, and you can still do similar things like that. Now, as far as trying to iterate over a data set in parallel with a parallel for loop, that's probably not going to be possible because, again, if you would do it in a multi-threaded scenario, you could do it in the parallel scenario as well. But if you can't do it in a multi-threaded scenario, or it's dangerous, or not recommended, it's not recommended in a parallel scenario either.
Is the parallel programming library used anywhere in the RTL itself?
Currently, we're not using it, but we are using it in the in our EMS server stuff. We're using it internally for some of our work for doing, our I guess it's called the EMS server, whatever it is that we're working on as well. But there is some other work internally going on for future stuff to actually start leveraging the library even internally. I'm actually personally working on some asynchronous programming stuff on some other related things as well. So not currently, mainly because it came in about the same time as everything else, so our ability to leverage it internally was limited for this first release, but we do tend to leverage it moving forward, yes.
Okay. So the request for more examples of tasks for each, or for tasks, loops, etc. I know Danny Wynn had a lot of examples in his session, and they're working on updating the documentation more.
Yes, yeah, we're constantly updating and fleshing out documentation, providing more examples.